Okay, so let's continue. At the previous lecture, we have started to study extensions of G biarbitrary group, not necessarily abelian, and we have seen that if we have an extension, then such an extension induces a homomorphism from G to the group of automorphisms of X. And so the problem is to describe all extensions of G by X modulo isomorphism of extensions with given G, X, and psi, or psi is such a homomorphism. Well, we have shown that if there is some extension, then in fact there are extension, then there exists f from G times G to X and gamma from G to the group of automorphism of X, which is not homomorphism that lifts psi, yes. Such that E is isomorphic to G gamma f X, where this group is, as I said, G times X, and has multiplication defined by the formula GA times HB is equal to GH, and then f of GH gamma H of A B. Yes, and moreover, this f and gamma satisfy the conditions these conditions are equivalent to the fact that this one is a group and that gamma lifts psi. So they satisfy the conditions. First condition is that gamma gamma y gamma x is equal to mu f x y. Here nu f x y is is the inner automorphism defined by f x y. Gamma xy, and the second condition says more or less that f is a cocycle, but not cocycle because x is not an abelian group, so it's not a a G module. This condition is f of x, y, z, gamma z of f of x, y is equal to f of x, y, z, f of y, z. So now let us suppose that we have g, x, and psi from g to out of x, and we want to understand if there exists some extension of g by x that induces such a homomorphism. Well, first of all, since this map is surjective, we can choose some lift of psi, which is a map of sets. Then, since this composition is homomorphism, we have that the class of gamma y, gamma x is equal to the class of gamma xy in the group of automorphisms. So it is equal to gamma xy, and on the left we multiply by some inner automorphism. So it's equal to nu f xy, gamma xy, for some f from g times g to x. And if, well, for convenience we choose gamma in such a way we choose gamma such that gamma of 1 equals to id x. And in this case, we can choose f in such a way that f of 1x equals to f of x1 equals to 1 for any x from G. Well, so if so, we automatically have 1. 1 for gamma and f. So if we have 2 by some reason for f, then there exists some extension, as we told before, and this extension is this guy. So the question, but if this quality is not satisfied, this doesn't mean that there is no extension, because we have some liberty in choice of f. This quality doesn't define German f uniquely, yes. So, but first let us check if this equality is satisfied. What?
Can you explain why first equality?
Because this is how we have chosen f. Gamma y, gamma x is gamma xy modulo some up to some inner automorphism. And we inner automorphisms knew something, yes. And we define f of xy as this element, some element, such that gamma y, gamma x is equal to to the inner automorphism determined by f of xy times gamma xy. And this is exactly equality 1. So they want the equality to be satisfied, but of course it's not clear why it's satisfied. So let us try to deduce it. How we deduced? We have deduced the this such type of equality before. We have checked some associativity. Here we have associativity too. Yes, we have associativity of multiplication of gamma. So we have gamma z, gamma y, gamma x. Yes, and we first can compute this one, and then we can write it as gamma z, gamma y, gamma x, and compute in another way. And probably we will get equality 2. Well, let's see. So we want to change everything, to replace everything by gamma xyz, of course. So here we replace first this by gamma yz, and to do this we need to add new f of yz, yes, and gamma yz, gamma x, and applying the same trick here, we get new f of yz, new f of xyz, gamma xyz. So let us do the same thing here. It is gamma z, new f of xy, new xy. So now we need to interchange these two guys, and you know that if we have some automorphism and an inner automorphism, we can interchange them, and in the inner automorphism this guy will be changed by gamma z. Yes, so it is new gamma z f of xy, gamma z, here gamma xy, and here we again apply our equality, and we get new gamma z f of xy, new f of xy z, gamma xyz. So we can delete gamma xyz on both sides and get the equality new here, guys, interchange xyz f of yz equals to new gamma, new f of xy z, gamma z f of xy. So it is almost equality 2, yes, except the fact that here we have also new. So these two guys are not equal, but the inner automorphisms determined by them are equal, and this means that they differ by some element of of x that induces an identity in the automorphism. Yes, and such an element is an element of center. Yes. So we have f of x, y, z, gamma z f x, y equals to f of x, y, z, f of y, z times k of x, y, z, where k is some map from g times g times g to the center of x. And you can easily see that it is normalized in the sense that k of 1 xy is equal to k of x1y is equal to k of xy1 is equal to 1x. So, since the center of x is an abelian group, k can be considered as a 3 cochain. So k can be considered as an element of what's called C3 of G Cx. Yes. And we want, so we are interested if we can replace gamma and f in such a way that k becomes unit, like identically unit. So if we can change them in such a way that k of x, y, z is 1x for all x, y, and z. So to do this, we to understand if we can do this, we will prove 3 lemmas. First lemma is that k is a 3 cocycle as an element of as a 3 cochain with coefficients in Cx. The second lemma is that if gamma is fixed, and we or I f we write f, but in such a way that the first equality is still satisfied, then we can replace k by any cocycle homologically equivalent to K. And only by them. In other words, if we have fixed gamma and we take some f satisfying the equality 1 and some f prime satisfying the equality 1, then cocycles k and k prime that we will obtain will represent the same element of the third cohomology, the coefficient in Cx. If gamma f give us k, gamma f prime give us k prime, then k minus k prime, the class of k minus k prime in H3 of G Cx is 0, and if gamma f give us k and k prime from Z3 G Cx is such that the class of k minus k prime in H3 is 0, then there exists f prime such that gamma and f prime give us k prime. It's the same thing what is written in lemma 2, but
Cx is regroup on X?
no, Cx is the center of X. To write H3 of G something or Z3 of G something, we need abelian group on the second position. So, okay. I think let us prove the first two lemmas and then we will formulate the third one.
Can you please repeat the definition of K?
Huh?
Can you please repeat the definition of K?
Well, we have shown that this n automorphism is equal to this n automorphism. So these two guys differ by some element of the center. And we denote this element by k of x, y, z. So k of x, y, z is this times the inverse of this. In any order, because k in the center. So we'll just prove lemma 1. To do this, we consider the following element. We consider f of x, y, z, t times gamma t of f of x, y, z times gamma z f of xy. And we will calculate it in two ways. The first way is to replace here this element due to this equality, yes. So we will get that this guy is equal to xy z t times gamma t of f x y z f of y z, and here gamma t k of x y z appear. Okay, and now what? Now we can write this in such a way, yes, and apply the same equality to this. Yes, so here we have x, y, z, and t. So it is equal to f of x, y, z, t, f of y, z, t, gamma t, f of y, z, and here appear k of x, y, z, t, and still this. Okay. Gamma t, k of x, y, z. And finally we apply here. Here we have y, z, and t, so we'll get f of x, y, z, t, f of y, z, t, f of z, t, and here we have k of x, y, z, t, and since Cx is the center, it is abelian, and we will write with addition plus, sorry, let's first write this one, yes, k of y, z, t plus k of x, y, z, t plus gamma t k of x, y, z. So here addition is the same thing as multiplication, yes, in the group X. So now let us do in another way. So first we apply our equality to this. Then we get again, not again, f of x. So we apply to this, it's xy, z, and t. So it is, sorry. So it's x, y, z. Sorry. And, here it was this way, yes. So we have applied to, no. yes, it's x, y, z, t times f of one minute. Sorry. Okay, here it's written in another way. So it's f of x, y, z, t again, because here, no. Okay, let us do as in my on my paper. So we don't do something here. We first replace this by gamma zt. So it is f of x, y, z, t, gamma t, f of x, y, z. And now we replace gamma t times gamma z by f of z t inverse gamma z t f of xy, yes, sorry, and f of zt. So this guy is equal to nu f of zt gamma zt f of xy, yes. So it's exactly the application of any homomorphism defined by f of zt. So now we replace this guy, yes. Okay, so we can replace this. So it we apply to x, y, z, and t. So it will be f of x, y zt, f of sorry. Here x, y, z, and there y, z, f of zt, yes, and the rest f of zt minus 1 gamma zt f of xy f of zt and here appears k of xy zt. So let's continue. Let's write again. F of xy zt. F of zt cancels, yes. So it remains gamma zt f of xy. F of zt and k of xy zt. So gamma zt, f of zt is there. So we hope that here we will get this part. We apply again our formula and get to x, y, and zt. So we get f of x, y, zt, f of y, zt, f of zt. So we replace this part, yes. And here we get k of xy zt plus k of x, y, zt. Okay. So this part and this part coincide, so we get the equality k of, let's write it in the right order, yes, k of y zt minus k of xy zt plus k of x, y, zt minus k of x, y, zt plus gamma t k of x, y, z is 0. 0 is the same thing as 1x, of course. But when we calculate in the center, we write 0 for 1 instead of 1, yes. And this exactly means that k is a tricocycle. Okay. So let us delete this, delete this. This we will save because we will use it. It's the definition of k. So the first lemma is proved. Let's prove the second one. So we want to prove that if we fix gamma and vary f, then k varies through the homological class of k. But what's the definition of f? The definition of f is that gamma x, gamma y, gamma x is equal to f of nu f of xy times gamma xy, yes. So if we can replace f by any f prime such that like f of xy, f minus 1 f prime such that new f of xy equals to new f prime of xy, yes, and only by such f prime we can replace. So we can replace f by f times h, where h is from g times g to the center, yes, because to have the same inner automorphism we need two elements differ by an element from the center. Thus we have f of xy equals to f prime of xy equals to h of xy times f of xy, where h of xy lies in the center for some h. So it's written here, h from g times g to the center. And so we put this in this formula. So what we will get? We will get that k prime of x, y, z times f prime of x, y, z times f prime of y, z is equal to, well, I'm not sure that what I do is necessary, because it's quite obvious from the form that it's written. It's not, it will take a lot of time. So here f prime, and now we have to put this instead of f prime, and we will see that k prime of x, y, z times h of, we can write the sum, plus h of x, y, z plus h of y, z times f of x, y, z, f of y, z is equal to h of x, y, z plus gamma z h of x, y. And here f of x, y, z, f gamma z, f of x, y, which is equal to this, yes, f of x, y, z, f of y, z multiplied by k of x, y, z. And so this and this cancels, and we see that k prime of x, y, z is equal to k of x, y, z minus h of y, z plus h of x, y, z minus h of x, y, z plus gamma z h of x, y, which is k of x, y, z plus delta h of x, y, z. And since h is arbitrary, is an arbitrary cochain, we are done. Element of 2G6 okay, so in fact we have proved that if the homological class of k is 0, then there exists extension because we can replace k by 0 in this case, yes, and we will have equalities 1 and 2. That is enough. Also, we have proved that if we don't vary gamma, then only cocycles that represent 0 in homology we can replace by 0. But the only problem that is still not clear is could we vary gamma and change the homological class of k? So it remains to prove the last lemma that says that no, if gamma f satisfies the equality to 1, which is gamma y gamma x is equal to nu f of x y gamma x y, yes. And k is determined by 3. Let's call this 3, yes. And gamma prime is another lift of psi, in the sense that gamma prime is an hour map from G to the automorphism group such that the composition of the projections gives psi. Then there exists f prime such that gamma prime f prime satisfy 1, the same equality, but we replace gamma by gamma prime, f by f prime, and replacing f by f prime in 3, we get valid equality. Well, what does this lemma say? say? It says that if we vary gamma prime, then of course we have to vary f prime, and we can do this in such a way that k will not change. And since and this means that when we vary gamma and gamma prime, we only can get cocycles, 3 cocycles from the same homological class. Yes, because we vary gamma to gamma prime, f to f prime, but there is some f2 prime such that gamma prime, f2 prime define k, and as we have shown in this case, like k prime and k are homologically equivalent. So the proof is of the same manner. It is quite technical. So how can we replace gamma? Yes, we can replace it in such a way that gamma x and gamma prime x have to differ by an inner automorphism. So gamma x prime is equal to nu g of x times gamma x for some g from g to x. Yes. Not to the center, of course. And then now we want to calculate what can f prime be. So we want to calculate gamma prime y, gamma prime x, and it is nu g of y, gamma y, nu g of x, gamma x. So we can interchange gamma y and nu g of x, then we will get nu g of y, nu gamma y g of x, gamma y gamma x, and this guy can be replaced due to the definition of f. So we will get nu gamma y g of x, gamma y, nu f of xy, gamma xy. And now we need to again replace gamma by gamma prime. So we'll get nu f of xy. Okay, let us write what we will get, then make some change. Gamma y g of x, g of y. And here we get gamma xy prime multiplied by nu g of xy minus 1. Yes. So we can put this here. Write here g of xy minus 1. So we can take f prime of xy is this guy, g of x y minus 1, f of x y, g of x, g of y, and direct calculations that are similar to all calculations that I have done today. Shows that f prime of x, y, z, gamma z prime f of x, y is equal to f prime of x, y, z, f prime of y, z, k of x, y, z. Let it be an exercise, yes. So the proof is finished. We of course have to put the definition of f prime here, put this definition of gamma x prime here, and use this formula and get right equality. So finally we get a theorem. Given x, g, and psi from g to the outer automorphism group of x, let us choose gamma x from psi x, define f of x, y by the equality gamma y, gamma x is equal to nu f x y gamma x y. So this equality doesn't determine f, but there exists f such that this equality is satisfied. Let us pick someone, then and define. So here we choose gamma prime and gamma and f, yes, and
Gamma x in psi x.
Like psi to an element x of g, it put in correspondence a class of automorphisms, yes, and define k of x, y, z by the equality f of y, z minus 1, f of x, y, z minus 1, f of x, y, z, gamma z, f of x, y. Then k represents some element of the third homology of G with coefficients in Cx, and there exists extension of G by x inducing psi if and only if the class of k in H3 is 0. By this reason, elements of H3, G something, are called sometimes abstractions to construct extensions. Well, it's not very good at this point to call them in such a way, because we don't know if we take some element here, is it abstract some extension. And, probably today or the next lesson, a practical lesson, we will show that in fact all elements here in some situation abstractions to the construction of extensions. Okay, so the final theorem here is the following. If there exists some extension of G by X inducing psi from G to out of X, then the isomorphism classes, isoclasses of such extensions are in one-to-one correspondence with H2 G CX. So if we have such a homomorphism, yes, then in fact this homomorphism of course induces psi induces psi tilde from G to the automorphism group of Cx, yes, and hence it induces G module structure. You will not see this. And hence introduce G module structure on Cx. So this guy makes sense. That's the reason. Because of course any automorphism of X induces an automorphism of the center, and if two automorphisms of the center differ by an inner automorphism, then they are equal, because in the center any inner automorphism acts identically. well, it has to be very easy. Let us call it sketch of proof, but probably it's a proof. If G gamma f x is some extension of G by x, so we know that that if there is some extension, then it is of this form, and we can put any gamma here. Yes, only f we have to choose. Then all other extensions are G gamma f plus h x, where h from G times G to Cx is a Tuka cycle and G gamma f plus h x is isomorphic. As an extension to G gamma f plus h prime x if h minus h prime is a coboundary. And this finishes the proof. So, modulo the fact that I told some facts but haven't proved anything. But probably all of this is quite obvious after what we have done before. Yes. Well, if we want to choose another f, yes, we have to replace it by, we have to multiply f by f of xy by some element of the center, yes. So we get h. And to have still a group, h has to preserve the equality 2, which almost means that f is a cocycle. So h has to be a cocycle. Yes. Here I think that times h is better. Here h prime, h. Yes. Well, so the only problem is why two such guys are isomorphic if and only if h minus h prime is a coboundary. Well, let be exercise. I haven't approved right now, but it's not very difficult. probably there is another way, but there is a way to look at these extensions, yes. Like both of them are g times x and element g0 and another g times x as a set. Yes, and to have a an isomorphism of extensions element of the form 0x has to go to 0x, yes, because x is a subgroup and it has to be fixed. And element of the form g, 1x has to go to 1x, and element of the form g1 has to go to element g, and here something like let be a, here x. It is more according to what we have done before. And here some g of x, and then comparing like multiplication here and here, you will see that g has to be a coboundary that differs h at h prime. Okay. So we have finished with the theory of extensions for a while, and let us go to another topic. In particular, this theorem says us that if you have some group G and some group X with trivial center, then extensions of G by X are parameterized by homomorphism from G to the outer to the group of outer automorphism of X, yes, because for any homomorphism we can construct a unique modular isomorphism extension. So the next topic is unit formulas and universal coefficients theorems. So Kenneth formulas serve for such kind of questions. Let we have a complex x and a complex y, and for example, suppose that we know the homology of x and homology of y. Could we compute, like we know homology of x, we know homology of y. The question is how to compute the homology of x tensor y, or like x is a complex of right arm modules, y is a complex of x is a complex of left arm modules, y is a complex of x is the complex of right modules and y is the complex of left modules. Or another question is, suppose that x and y are complexes of right modules. We know the homology. Could we compute the homology of complex hom R x y? We have not defined this complex, but we will define it probably today or the next lecture. So,
You didn't write homology. You just wrote home, not homology.
Sorry. So, partial answers to this question give Kuhneth homology theorem, Kuhneth formula for homology. This guy question, and here Kuhneth formula for cohomology. Before we will prove the Kuhneth theorems, we need some basic facts that I missed before. And the fact is the following. It's lemma. Let we have three complexes. U dot, V dot, W dot, and morphisms of complexes U dot, V dot, here G dot, W dot. So two morphisms, F dot and G dot, such that for any I, for any integer I, ui, fi, vi, gi, wi is a short exact sequence then there exists homomorphisms delta I from the ith homology of W to to I minus 1th, I plus 1th homology of W to ith homology of U, natural in U and UVW. Sorry. Wait, what does this mean? well, this means that if we have like u prime, v prime, w prime, and have morphisms of complexes from u to u prime, from v to v prime, from w prime, such that everything commutes, then of course these morphisms of complexes give homomorphisms between homology, and we have here commutative square, more or less, yes. Well, later I will write what does this mean, if it will be required. Well, and what is important is that there exists a long exact sequence. Such that there exists a long exact sequence h I plus 1 w delta I h I of u, then h I of f to h I of v, then h I of g to h I of w, and again delta I minus 1 to h I minus 1 w of u. Let us prove this lemma. So we need to define delta I. Yes, so let us pick a part of this diagram. So we have here w I plus 1. Yes, here v I plus 1, u I plus 1, here u I, v I, w I, here it's f I plus 1, g I plus 1, f I, g I. These maps are monomorphism, this map epimorphisms. Here d ui, d I, d wi. So we need to construct a map from the I plus 1th homology of w to the ith homology of u. So if we have some element in the I plus 1th homology of w, it can be represented by some element of w I plus 1, yes, such that di w of this element is 0. But since gi plus 1 is epimorphism, we may assume that this element is of the form gi plus 1 of v, some v here. So gi plus 1 of v satisfies diw g I plus 1 of v is 0. Yes. Then we can apply di to v and get div of v. And since this square commutes, this element goes to 0 here.
So we pick such v so that di of it is 0.
We in fact pick some element in wi plus 1 such that di of it is 0. But this element is of the form gi plus 1 of v, because this is epimorphism. V is not well defined. The element here is not well defined because different element can represent the same element of homology, and V is not well defined because different element can go to the same element. So we will need to check well definedness of what we will construct. But we can do this. So it goes here, and since this goes here, there is some element delta I g I plus 1 of v that goes to div of v. So it satisfies d delta I g I plus 1 of v. If we apply to it fi, we will get div of v. Yes. This is a way how we define delta I on gi plus 1 of v. So first of all, we need to show that we really get some cocycle, some cycle. Yes. So we need to show that d we need to show that d I minus 1 u delta I g I plus 1 of v is 0, but if we multiply it by fi minus 1, yes, here u I minus 1, fi minus 1 is 1. If we multiply it by fi minus 1, which is monomorphism, then we will get, by commutativity of the square, what we will get? We will get d I minus 1 v fi delta I g I plus 1 v, and this guy by this formula is div, so it is d1 v div of v, and it is 0 because the composition of differentials is 0. So really we get an element, like some element that determines some class in the homology. So we need now to show that this element does not depend on the choice of the class of homology. In homology, doesn't depend on the choice of v and on the choice of gi plus 1 of v. Yes. So first of all, if we have some v prime such that if prime is such that gi plus 1 of v prime equals to gi plus 1 V. Then, in fact, V prime is equal to V plus Fi plus 1 of U. Yes, because this sequence is exact here. And so when we apply div, we will get div of v plus div times this fi diu of u, and hence using v prime we will get delta I g plus 1 of v prime is equal to delta I g plus 1 of v plus diu of u. So the homological class is the same. Well, and if we want to choose another element here representing the same homological class, this means that their difference is a boundary, so it comes from there. From there it comes, can be has preimage here. Yes. So if w from w I plus 1 is okay, I don't want to introduce my notation. So if we take d I plus 1 w of w, then there exists v such that w is equal to g I plus 2 of v, then dA plus 1 w of w is equal to g I plus 1 d I plus 1 v of v. Yes, and hence here on the role of v we can take d plus 1 v of v. When we will apply di, we will get 0. Yes. Well, we can make this construction in such a way that we will get 0, but as we've shown, then how you make construction doesn't change the homological class. Okay. So it remains to show that the sequence is exact. And it is like some diagram chase. And let us leave it as an exercise. Well, so I only will say why the compositions are zero, because it is quite easy. The compositions are zero because the composition of hi of g and delta I minus 1 is zero, because what does mean that element lies in the image of hi of g? This means that it can be represented by a cocycle of the form gi plus 1 of v, where v is cocycle. Can be represented by a cycle of the form gi plus 1 of v, where v is a cycle itself. Then by our construction we get 0 here and then 0 here. And to show that the composition of delta I and the ith homology of f is 0, we simply see that the element that we get here, which is delta I j plus 1 of v, by definition, well, when we apply fi, we get div of v, which is 0 in homology. So the compositions are really 0, and it remains to check the exactness. It is a little more complicated technically, but not very difficult. So we'll leave it as an exercise.